All right, guys, so let's go ahead and get started. So today we're talking about the CCNA and Cisco certification. So pretty much what can it do for you essentially? So Cisco certification, what is it? Why the Cisco certification? So a lot of you that are already in class today understand the why. It's maybe I want a job, maybe I want to get started in networking, maybe I want to promote, whatever the case may be. It all leads you down to one path, and that is I want to be a network engineer, I want to join IT in some capacity. I know a lot of my students sometimes are going to like WGU or they're in a cyber program and this is part of their cyber track. So just kind of a blanket statement, Cisco certifies IT professionals in multiple disciplines as it relates to the information technology industry and their own products, hardware, and software. And all that to say that Cisco certification obviously caters to the Cisco technologies, while also just talking about technology, period. Now today, or this next 2 weeks in our 10-day course, we're going to be covering the CCNA. So the technology that this falls under is called enterprise. And really what that means is routing, switching, wireless, some security, some WAN architecture, and of course automation now, automation and programmability. And we're at the associate level. So there should be some understanding that, hey, if I'm taking the CCNA exam, that I already know a little bit. Or at least I've learned some general IT. I've done like an A+ or a Net+. You can't jump straight into it off no knowledge. That's kind of what I did when I was starting out. I was in the Army. I got deployed to be a help desk guy. Never had formal IT training. I was a SATCOM, so I knew about antennas and shooting to geosynchronous satellites. And they said, you're going to do help desk. And then they made me do networking, and I literally had no idea. This was before AI, so I was just Googling things and trying my best. And then I jumped right into learning about the CCNA so I could get better at my job. But it is possible. So where I like my students to be is have some level of knowledge in IT before jumping into the CCNA, but if you don't, that's okay. Okay, so what does certification mean for you? Now this is just kind of like a fun slide I put together. Why should you get certified? We kind of already went over that. First job in IT, making a change in your IT career to help for a college degree, for current career improvement, or to raise for your current role. So there's so many reasons to get the CCNA. Like in my day job, our tier 2 network admins, they need the CCNA. So I know some have been hired with just a Sec Plus because that's what's required, in the DoD, Sec Plus to be an admin on any capacity on a DoD information environment. And then they have to get the CCNA. And usually when they get the CCNA, then they get a little raise, like 5-10 grand raise, whatever. This is just a little slide I like to put in there, average salary for CCNA. This is all going to depend. Like I said, our tier 2s cap out at 90K. So we have tier 2 network admins making 90K, and they just have a CCNA and maybe some years on the job, years of experience. So this is going to vary a lot. Okay, so that's just getting that out of the way. Now we're going to jump into some real learning, okay? So now we're going to jump into some networking stuff. So intro to networking. So what is networking at a very high level, big picture? It's kind of like an all-encompassing term which refers to the design, management, maintenance, and operation of network infrastructure, software, and policies, okay? So what do we mean by that? What we mean by that is that the CCNA, networking professionals, their whole job is to make sure that your traffic gets from point A to point B. And that's it, right? It's how do I get this data, this packet, this end user to this web server? And all the management, maintenance, installation, monitoring, logging in between, that is networking. And there's so many different ways that happens. And there's so many different components in network infrastructure. So network professionals install, maintain, manage, and troubleshoot the infrastructure that enables data to traverse the globe. So the internet being the largest network, which I think this number has gone up now, with 5 billion daily users. So networking in the enterprise. So what do we mean by that? So networking in the enterprise is typically where we all start out. And I'll try to break this down in like layman terms. When you go to work, you hop on your company workstation, your company computer, and you log into your company Teams that reaches out to Office 365, and you go on your company portal, and you go on your company time card website, you go to your HR website, you're emailing, all that company enterprise stuff, that is the enterprise. That is, I'm in a spoke office, the HQ's over here, and I can Teams chat someone in the HQ office. All that is called the enterprise. So a lot of times, your first job as a network engineer, you're not running the internet. You're not making BGP changes on an ISP edge, provider edge router. Most of the time, that's not our first job in networking. It's more like campus. It's more like LAN. It's more like setting up access points so that your roaming Wi-Fi users can go through anywhere in your office building or your campus and get access to the internet and access to company resources. So network professionals do most of their work in the enterprise. That's where a lot of us go. There's data center, there's cloud now, which again is part of the enterprise really now. If you think about it, your company pays for it. It's part of your company enterprise. The enterprise is something that's known as an intranet. That's something that's what the organization maintains. And that's really what you're maintaining. So I have here a little diagram. This CE stands for customer edge. So when you're a network admin, network engineer, you're doing everything at the customer edge and downstream, okay? Customer edge and downstream. And maybe the only thing you manage at your demarc point here is the IP and the static routing protocol sending out to the ISP, or the VPN tunnels, IPsec tunnels you're building to the other customer edge routers, right? But that's really it. You're on the customer edge, you have a demarc point, and you're ensuring that your customers, your employees have availability, and you're doing that by maintaining your network infrastructure, okay? So a typical CCNA will start his or her career working on network infrastructure in what we call an enterprise. And sorry if it seems like I'm talking fast, we have a lot to get through here in day one. History of the internet, it's not really too important, it's not gonna be on the exam, but the very beginning of the internet started with ARPANET. It used NCP for switching packets. I kind of just like to throw that in there, it's not on the exam. But TCP/IP back in 1983, and that's still the protocol suite that we use today to get traffic from one point to another, from endpoint to endpoint. We still use the TCP/IP protocols. So your role in networking. So as a CCNA, it is your job to ensure that the critical infrastructure that connects us stays online. You make sure the internet stays on. Essentially, at the end of the day, when you go into your workplace, wherever it is, and there's a sales guy, a marketing girl, HR, all that matters is that they're connected. That's all that matters. They look at you as the guy or girl that keeps them connected, that keeps their Wi-Fi good, right? That's pretty much the CCNA network engineer's role, okay? I go through those slides pretty quick because it's like, let's start getting to the learning, the meat and potatoes, okay? So now, actually, let's start learning about some networking infrastructure and components. So network components. So network infrastructure. So network professionals will manage and maintain key network hardware. And in this course, we're going to focus on the network components that Cisco wants us to learn about in the CCNA exam objectives. So we're going to start off at the layer 2. What is a switch? And I'm going to actually stop sharing my screen here, and I'm going to go to my whiteboard. Okay. Now, guys, don't be too careless. Don't be taking over my mouse here while I get into this. Okay. So the first network component we're going to talk about is a switch, and particularly we're going to talk about a layer 2 switch just to start, because I'm going to teach you the basics of switching. So this network component, this network infrastructure, a switch, is what connects our LAN, our local area network. So a switch connects our LAN. It also is the first stop to connect our users to the enterprise/internet. So when you plug in your computer into the wall, into that Ethernet jack, people will call it an internet cable, whatever, the Ethernet jack, the RJ45 connection, that is going to connect to what's called a switch. There's many types of switches, and what I mean by that, how we build the architecture, there's access, distribution, and core layer switches. But in this, I'm going to go over fundamentally how does a switch work. So let's take a breath, and let's talk about a MAC address real quick. So I'm going to draw something out here. I'm going to grab my pen. Let's start out with, I don't want that magic thing on here, a switch. So we have our switch. I'm going to call it SW for switch. That switch is going to connect our users. I'm just going to start off here with like a laptop, okay? And that laptop is going to have a NIC right here, okay? That's its NIC card. That NIC card is going to have what's called a burned-in address, or a MAC address, immediate access control address. That is a layer 2 address. That's what defines that NIC, which then defines that computer with its layer 2 address. So this NIC right here has a MAC address. And that MAC address is what we call hexadecimal. It's 12 hexadecimal digits. So hexadecimal is 0 through F, right? So 0 through 9, and then A through F, okay? So a MAC address may look something like this. 00.AA.00.11 :12 :EF. Okay, that's a MAC address. So this is switching. This involves switching, okay? So a switch, in essence, is switching MAC addresses. So I'm going to go through the flow here, okay? So on my computer, we'll call this PCA, wants to talk to another PC on its LAN. And it's going to talk to the switch first, okay? It wants to talk to PCB over here. PCB. What's going to happen is that computer is going to generate a layer 2 packet, what we call a frame, okay? Or a layer 2 header. Well, a layer 2 packet, but it's going to have on there a layer 2 header. Okay, and this is a frame. This is what the switch is going to route for you, or switch for you, actually. And then, of course, we have our data payload. So this is our data. Let's just say that's 1472 bytes. This will come into play here because MTU, maximum transmission unit, is like 1500, right? Okay, so that layer 2 header. That layer 2 header is going to have a source MAC address and a destination MAC address. So check me out here. I'm going to say PCA's MAC address is just BB for brevity reasons. I don't want to write out 12 hexadecimal digits, okay? Or we'll say this one's AA. So the source is going to be AA, okay? That's the source MAC address here. And then the destination, let's say we want to talk to PCB. Whoa, sorry about that. We want to talk to PCB, and that MAC address is BB. So we put that in the destination. Now I'm going to create this frame with my data payload, and I'm going to send that off to the switch. Now on this switch, I'm going to have this interface labeled here. So at the switch, this could be like gigabit Ethernet 0/11. Okay, so I'm connected to port 011. And I'm sending my frame off with a source MAC and a destination MAC in my layer 2 header, okay? That switch is going to have something called a MAC address table. Now here's the meat and potatoes. This is the brain of that switch. The MAC address table is going to tell that switch how to switch traffic, how to switch frames, how to switch data from, its ports, from its interfaces. So this is called a MAC address table, or sometimes called a CAM table, a content addressable memory table. So we're just going to call it MAC table. Okay, that's the MAC table, sometimes called CAM. And I'll just type that out so you don't have to, my bad handwriting. So CAM, because sometimes it comes up like that. Content addressable memory table, all right? And that's synonymous with MAC address table. So when the switch receives that frame, here's what it's going to do. And this is very important. This may come up again. This may be on some practice questions. When a switch receives that frame, it's going to take the incoming MAC address. That's the source MAC address in our layer 2 header. It's going to take that incoming MAC address and say, I'm placing you in our MAC address table. So hey, PCA is connected to me on port 11. I have an incoming frame from him. I'm going to populate my MAC address table with its information. So I'm going to say on port gig 0/11, we'll have a VLAN too. Well, we won't put that for now, but there will be a VLAN in here. On port 011, we have MAC address AA, okay? Now let's say PCB had already communicated with that switch. So the switch knows that PCB is on gig 07. So let's say it already has PCB on port 07. So it's going to do two things. If it doesn't already have that computer in its MAC address table, it's going to insert it. It's going to say, cool, source MAC address, incoming frame. Boom, you're in my MAC address table now. MAC address AA, you're on port 11. Boom, done. It's then going to look at the destination MAC address in that layer 2 header field. And it's going to say, hey, you're destined for BB? Well, great. I just looked at my MAC address table, and I know where BB is. It's on gig 07. So I'm going to switch you out gig 07. And then it's going to switch out to gig 07. That is switching at its most basic function and form, guys. It's taking ingress frames, looking at the source MAC, putting that onto MAC address table, then looking at the destination MAC and saying, do I know where that is? Do I know where that destination MAC address is according to my MAC address table or my CAM table? I do? Awesome. I'm going to switch it out that interface, okay? And that's it. That's switching. So now you may say, well, Johnny, okay, what if this happens? What if the switch doesn't know where the destination MAC address is? What if it has no idea? What's going on here? What does it do then? Well, if it doesn't know where the destination MAC address is, so it's not in the MAC address table, it's going to send out a broadcast MAC address. So hear me out. Check me out here, okay? So if the switch does not know the destination MAC address for an incoming frame, it doesn't know where the MAC address is, the destination MAC address, it's going to do this, guys. And I'm going to type this out for you as well. It's going to forward a broadcast frame now, a broadcast MAC address, out every active interface besides the one it came in on. So give me a second while I type this out. If the switch does not know where the destination MAC address is, let me shorten this here. Hold on. Okay, so if the switch does not know where the destination MAC address is, it's going to do this. Forward out a broadcast frame to all active interfaces. I'm going to put it in all caps, besides the one it came in on. So it's going to forward, I don't know what happened there, forward a broadcast frame to all active interfaces besides the one it came in on. The broadcast frame, the destination MAC field is all Fs. So a destination MAC address for a broadcast, so a broadcast MAC / frame is literally this, guys. All Fs. I'll put it how like a Cisco device would read it. All Fs, okay? So what's going to happen is the switch is going to say, hey, I see you're trying to reach BB, but I have no idea where that is. So what I'm going to do actually is I'm going to convert that layer 2 header into this. The source MAC is AA, but now the destination MAC is all Fs. Okay, all Fs. And I'm going to send that out all active interfaces besides the one it came in on. So then when it actually goes out gig 07, PCB responds to that broadcast because all devices in a broadcast domain respond to a broadcast message. And then when it responds, well, guess what? When PCB builds its frame, it builds a layer 2 header, it puts its MAC address in the source MAC address field. What does the switch do with that? It inserts it into the MAC address table. Boom. Now we know where it lives. That's what a switch does when it gets an unknown destination MAC address, okay? Awesome. So that is layer 2 switching as bare bones as I can make it. Now a switch also can be layer 3. So we can also have multi-layer switches as well, guys. So a switch doesn't just do this switching with its ASIC chips, that's the compute module in a switch that does this fast switching. It's not CPU based. The MAC address table runs off CPU, which will come up in layer 2 security when we go over like DHCP snooping. But the CAM table runs in like CPU. And then the actual switching data plane is in something called ASIC chips. Now, A switch can also be layer 3. And then that's when it builds something called a TCAM. It's like tertiary cam table. It's not going to be in the exam, so I don't want to get ahead of myself. But a switch, let me move this over here so you can see the notes. A switch can also be layer 3. It can do routing. Sometimes this is called a multi-layer switch. It can also sometimes be called a distro / distribution, or core switch. I don't think I spelled distribution right. That's okay. It's like distribution. It's going to bug my ADHD. Is that it? Yeah, there we go. Distribution, okay? So, it can also be layer 3. Now, layer 3, what does that mean? That means now we're not just going to switch frames using MAC addresses. That means we're going to route via the IP table, or excuse me, IP address. We're now going to build a routing table and route based off destination IP address. And the dedicated device that does this is called a router, but a switch can also have routing functions. And I've been in environments where that is true, where like the core switch sometimes will be your demarc point up to the ISP. So let me get some more like real estate here. Okay. And now, zoomed in a little bit too much there. All right. Now we're going to go over a router. So just to recap, guys, that was me going over the network component called a switch, okay? I'm going to do all this on the whiteboard, and then I'll hit the slides after and just like make sure I didn't miss any key points. But now we're going to go over a router, guys. And you know, as a network engineer, don't we love this, folks? We love routers, right? This is where we live, in the routing. Well, if you're a network admin, you sometimes live in the campus and like wireless. But I like routing, high-level routing, right? But we got to break it down for the CCNA level. So what does a router do? A router is the device, or a device that does routing. Sometimes it's your firewall, sometimes it's your switch, right? But a dedicated router routes IP packets to their destination anywhere in the globe, or anywhere in your enterprise. You know, try to keep it in a CCNA level, anywhere in your enterprise. So that's what a router does. Now, how does it do it? Well, Johnny, how does it do this? Let me make some notes, right? This is a dedicated layer 3 device that routes IP-based packets and uses its routing table. I'm going to make this look cleaner. Just give me a sec. Okay. Okay, this is what a router does. Pretty clear here, right? I think so. Let me get all this. Go down a little bit. Whoa. Okay, so how does it do this? Well, let's draw some routers up here. So I'm going to draw R1 and R2, okay? So I got R1 here and R2. R1 and R2. And they're going to be connected maybe over some serial interface, a fiber, whatever. And they're going to have here a shared segment, a shared Ethernet or a shared IP segment. So let's say they're on this network here. This will make more sense as we go on, okay? When we go over subnetting IP addressing. This will be .1, this will be .2. Okay, so that's how they're going to talk to each other. So IP addressing in the TCP/IP protocol suite. The IP address is how a device identifies itself on the IP-based network, okay? Where the layer 2 is that burned-in address that identifies like a NIC, identifies your Ethernet port at the layer 2, an IP address, which is also going to be assigned on your interface, your NIC, your Ethernet card, whatever, your wireless NIC too, is going to identify you, give you a unique address in your IP-based networks. So here, R1, let's say this is gig 00, and this is gig 00. R1 is .1, R2 is .2. Now, well, what's the whole point? The whole point of IP-based reachability and routers is to get end-to-end communication, end-to-end data packets being sent to each other. So, let's say R2 has some users. They're sitting on the 10.0.2.0/24 subnet. Okay? So I got 200, potentially 252 users here, right? If I save some IP addresses for the network and broadcast. Technically 254, but anyways. Then R1. I have this network sitting on my LAN. 10 dot, that's a 0.1.0/24. I got some users over here. If you ever see someone just make a line right here, guys, that represents like an Ethernet segment, something like a switch. So potentially there's switches in our LANs here, right? So both routers downstream have a LAN with users. Now let's say the users over here, all their PCs, their laptops, their phones, whatever, are in this network. So this computer's .10 and this computer's .20. So this computer has the IP address 10.0.2.10 and it wants to talk to its buddy over here. So I'll call this PCB and I'll call this PCA. PCB wants to talk to PCA and vice versa, right? PCA wants to be able to respond. Okay, so we need IP reachability. So what's going to happen in this flow? What's going to happen is PCB is going to build an IP-based packet. So in this IP-based packet, it's encapsulating. We're going to have layer 7 all the way down, but I'm focused on layer 3 right here, okay? So I'm not going to draw the layer 2, the layer 4, 5 headers. I'm just going to draw the layer 3 header. So we are going to build that. Let me get a good color here. So PCB is going to build its IP-based packet, and it's going to have an L3 header here, a layer 3 header, okay? And guess what? It's going to have a source IP and destination IP. And in the transit of this IP-based packet, these aren't changing. Now, I know you're going to, don't come at me. I know about NAT, but this is like the basic fundamentals. Without NAT, without like us running out of IPv4 addresses, this is how it would work, okay? Source IP and destination IP, they would not change because we need full reachability end to end, correct? Okay, so the source IP is .10, destination is .20. And of course, guys, we have our data payload, okay? Total MTU is 1500, so our data is probably like 1472 with all of our header encapsulation, adding, more data on top of that. Okay, so PCB, what you don't see here is a layer 2 header that's going to tell it to go to its default gateway's MAC address, but essentially, it's going to send this to the router. And then the router is going to receive that IP-based packet, and it has one job, to route that packet to its destination. So it's going to look at the destination IP address, and it's going to reference its routing table. And it's going to see, does my routing table have a route, have a known prefix match to this destination IP? And then that RIB, or that routing table, I'm going to draw this all out, is going to inform the forwarding information base, the forwarding table, about how to switch that packet out its routing device. So if it's incoming on gig 01, that's a gig, the routing table is going to look and say, do I have a match for that destination IP? If I do, tell my forwarding information base how to route that packet, switch that packet out of me, which is going out to gig 00, right? Okay. So you're like, Johnny, cool, but you taught us how a switch populates the MAC address table. How does a router populate the routing table? Here's the thing, guys. Routers are going to share routes with their neighbors. This is going to happen in a lot of different ways. What I'm going to tell you right now in this section is that somehow these routers have to tell each other about their networks. We can do this with static routes or dynamic routing. And then within dynamic routing, we have exterior gateway protocols and interior gateway protocols. And then within the interior gateway protocols, we have different types as well, like link state, distance vector, and advanced distance vector. All that is for day 5, okay? What you need to know here is that these routers build the routing table off information from its neighbors and its connected interfaces. Y'all ready? Let's build the routing table for R2, okay? So R2, it builds its routing table. Let's just say, for this example, R1 and R2 are sharing each other's routes with OSPF. So what that pretty much means is when they become OSPF neighbors, they build adjacency, blah, blah, blah. R2 is going to tell R1 about its users and its connected interfaces. It's going to say, hey, I have all these networks attached to me. Let me tell you about it via OSPF. R1 does the same thing. R1, if R1 and R2 are participating in OSPF, R1 also sends the same information. Hey, these are all my networks, okay, that I know about. Here you go, neighbor, because we're OSPF neighbors. Build your database, build your routing table. More on that later. So R2, first off, before any routing protocol is configured, we're going to input in there our connected interfaces. So on R2's routing table, we're going to have local and connected is what it's called. And we're going to be like, hey, connected to me, I have this network hanging off gig 0/1. And then I also have this locally and connected to me. I have the 1.1.1.0/30 hanging off gig 00. Okay, now we enabled OSPF now. Awesome. R1 told me about what it has. So now via OSPF, I learned about this network. I'm not going to draw the administrative distance or anything like that. We're just not ready for that yet. And I learned about this network via gig 00, right? So I learned about that network via gig 00. Okay, cool. I built my routing table. Obviously, it's a little bit more complex than that. That's in our routing section, okay? This is just the basics of what a router does at a high level. So now, when PCB sends that IP packet to R2, R2 is going to be like, okay, let me inspect that header. Bada bing, I have a match, right? You're destined, you want to talk to 10.0.1.20. Well, guess what? That IP falls within this network that I know about, and I learned about that network from gig 00. So guess where you're getting forwarded out, buddy? Gig 00. I'm going to send that packet out. R1's going to receive it, and what do you think it's going to do? R1's going to receive that, and it's going to look at its routing table. It's going to be like, oh, word? You want to go to 10.0.1.20? Well, that actually lives off my connected interface here. So I'm going to send you out there to your destination. And then when that PC replies, it builds its layer 3 header. And here's how it's going to look. It's going to be like, okay, I'm PCA. I need to reply to PCB. Here's my layer 3 header. Now my destination IP is the source, right? Now my destination IP is PCB. So that's .10. And now my source IP is .20. And boom, there we go, guys. So now it's going to go to its routing table, and it's going to do the same process. Does the destination IP, is that anywhere in my table, routing table? Yes, it is. Okay, I learned that off gig 00. Boom, send that out gig 00. Go to the next hop, and then take it. The next hop will take it from there. That's a router. That's a router in its full essence. Let me get some water real quick. Hold on. Trying to be enthusiastic, at least for the first hour, right? Okay. Now, that's pretty much it in its basic functionality. But does a router do anything else? Yes, it does. A router does VPNs, it does IPsec. It can even do like Call Manager Express. Cisco has ISR platforms, integrated service routers, that can do a lot more than just your basic routing, okay? But that's its main function, right? That's its main purpose, that's its main function. You could buy routers that, they used to have like, you could put hard drives in there to do NVR. I have a Unify Pro Dream Machine, it's a router. I have an 8 terabyte hard drive in there. I could have used that for storage. I used that for network video recording. So routers are capable of doing a little bit more, but their dedicated thing that they do is route IP-based traffic, okay? Alrighty, guys. Do I need to take a break? Here's what we'll do. We'll go over firewalls, and then we'll take a break, okay? So now we're gonna go over firewalls. So if you guys are any security guys in there, firewalls can do a lot. They can do LLM, large learning models, AI-enabled behavior heuristic analysis, and then do intrusion prevention and detection based off that AI-enabled user behavior baseline that's always growing and always being fed a threat feed so it can look for current exploits. Firewalls can do a lot nowadays. And then they have their basic layer 3, layer 4 filtering. They could be a VPN concentrator for like Palo Alto, what's it called? We literally use it at work, Global Connect. Cisco has AnyConnect. They could be an IPsec VPN concentrator. They do so much, but at its core functionality, besides all the additional advanced features that firewalls have now, making it kind of like a unified appliance, besides its SD-WAN capabilities now, like Panorama or FMC for Cisco, besides its SASE capabilities in the cloud now, at its core, what the CCNA wants you to know about is that a firewall filters traffic into your network and leaving your network. Boom. It filters inbound/outbound traffic. Very broad, but that's what the CCNA, I feel like it wants you to know about firewalls. It filters traffic inbound/outbound from your enterprise. from/to your enterprise. So typically, firewalls sit at the edge, right? They may be your customer edge. They may be sitting just in line from customer edge to provider edge, doing some sort of like sensor feature, just looking at like doing some deep packet inspection, okay? But at its core, it filters traffic inbound/outbound from and to your enterprise. There used to be a term, well, it's still a thing, next generation firewall. That used to be like, oh, this is our, from a vendor's perspective, our good one. And then here's our old firewall. Like Palo Alto and Cisco, now everything's a next generation firewall, right? So key things for the next generation firewall, it does advanced malware threat protection. It can do user behavior analysis and determine IPS, IDS based off heuristics. And this is AI enabled, of course, nowadays, right? Gotta throw that in there. AI enabled. Okay. It can also be a VPN concentrator. It can also do wait, I already put that, right? Malware threat detection, yeah, okay. Cool, that's pretty much it, all right? Now, a traditional firewall would only do layer 3/4 filtering, okay? Layer 4/3 filtering for a traditional firewall. And this would be stateful or stateless. We don't need to go into this. I'm just kind of writing it up there so you kind of like, you have the knowledge. And then layer 7 filtering would filter packets end to end, which when we're filtering packets end to end and we're doing some like URL inspection, deep packet inspection, what do we need? To do deep packet inspection, we need TLS decryption/encryption. Very important there, okay? Because end to end, right? When I go to a website and HTTPS, I did my TLS handshake, that's my session layer. I'm protected from the moment it leaves my workstation till it gets to my Wells Fargo account bank server. It's protected by TLS 1.2, 1.3, right? So if I want to see packets destined for the web, HTTPS, I'd have to decrypt them somewhere before it leaves my enterprise, right? To do that deep packet inspection, okay? So, what I'm about to draw is a design that's more geared towards a CCNA. So I get it, if you're doing like CCNP security, you're looking at other things, you're like, well, firewalls can be deployed in a lot of different ways, in the cloud now, whatever. I'm just showing you a basic on-prem deployment of a firewall and what it would do, okay? So just you get the best kind of, for the CCNA level. Common deployments. I'll just make it black, right? So your firewall here, okay? Here's your firewall. It's going to create zones, okay? This is like traditional firewall stuff. It's going to create a zone. We're going to have our inside zone. And this is also going to be our trusted zone. When we say trusted, we're essentially just saying like, hey, this is our stuff. So we're going to give it a different like trust level, a security level, let's say of like 100. So it's trusted, okay? That's our trusted zone. This is not in the CCNA. I just want to give you the best, And then, of course, this could be connected to like a router. And then we have our switch, right? And then it's also going to connect to the untrusted zone. This is your ISP. This could be, a direct connection to the cloud. And depending how you look at it, if it's your own cloud environment doing an IPsec tunnel or something like that, could be more trusted, but this traditional, right? This is our outside / untrusted. Let me fix that handwriting. Outside / untrusted zone. Okay? Now, why am I putting these terms up there? These are very specific to like traditional firewall security terms. The untrusted outside interface on that firewall, that's where we do of our in-depth filtering. That's where we do of our malware threat detection, right? If you're putting it to an interface, that's our untrusted zone, our untrusted interface. Because it's going to an outside network we have no control over, right? Then our inside trusted zone, that's our interfaces facing our LAN, facing our downstream, facing our enterprise, okay? And then sometimes we have something what's called a DMZ or screened subnet, depending on what exam you're taking. That's what CompTIA calls it, a screened subnet. Anyways, that's like our DMZ. This could be where you do some proxy services, but this could be like for services on-prem that need to face the public internet and face you as well. So this is like our DMZ, okay? I don't think they asked about that anymore really, but I just want to give you the most knowledge. Alrighty, that's all I'm going to say on firewalls. I've yapped for about 40 minutes straight. So for you guys in the Zoom call, let's go ahead and take a 10-minute break, okay? So I'm going to put a clock timer on here. Timer, 10 minutes. And yeah, we're going to take a quick break, okay? Just so I can rest my voice and stuff. So voice/brain break. Alrighty, let me
Cool
check.
beans. Hey, John, just, I got like 1 more hour, then I'm going to have to go, but I'll be back tomorrow.
Okay. Yeah, if you guys have to leave the Zoom session, then all good. All good. That's fine. Yeah, no worries. Everything's being recorded and it'll be uploaded to Google Drive, so.
Okay. Yeah, I'll catch up before tomorrow's class.
Okay. Sounds good, man. Thank you. Alrighty, let me check this TikTok live here. I already got like a notice that my live visibility is restricted because it contains unoriginal or reproduced content. Let me go ahead and appeal that bad boy. I don't know what that means. Can I not teach CCNA on TikTok? I don't know what that means. But if you guys in chat have any questions, just let me know. I'm like doing TikTok from my computer. I didn't know you can go live from there, so I think I can see other comments. Whew. All right, 10-minute break. Let's see if I can add some text to this so you guys can I can tell you what questions to add. No, I can't do it when I'm live. This is the first time I've ever live streamed on TikTok. I usually just do it streaming from YouTube, but I just learned that you can just like overlay the OBS camera and then like you can, do TikTok and YouTube at the same time, so pretty sick. But I will be cutting this live short because, I'm doing this Zoom call and these guys paid for the course, so I don't want to just give away everything for free. But I'll probably end the TikTok live and the YouTube live probably halfway through the course, halfway through the live session today, so probably around 7:30. But yeah, if you guys have any questions, just shoot them, I'll put a little bit more about myself in the next one, like, hey, I'm a senior network engineer. I run a certification company, and ask me anything about getting jobs in networking or the IT field or cybersecurity or anything about the DoD or GovTech. I've been in GovTech for 11 years, so I know a little bit about it. In my day job, I'm a senior network engineering lead. So I have a team of 6 senior network engineers that I have to pretty much put them on, lead them in deploying data centers, network infrastructure, white papers, things like that. But yeah, hope you guys enjoyed the stream, or enjoying the stream. I'm gonna check my YouTube as well. Hey, baby. What? Were you misbehaving? I'm on break, Amanda. You want to come? I'm live streaming on TikTok.
She pushed her sister really hard.
Don't push sister, honey. I'm on TikTok live. Oh. You want to get in the stream? Oh, okay. And I'm on YouTube Live, technically. Hey, honey. Hey, honey.
She said I yelled at her.
Yeah.
I did not yell at you.
Mommy didn't yell at you. You want to see? We're live right now. Hi, baby. Hold on. Huh? Don't be mean to your sister. Ugh. We got 6 more minutes, girls, and then we got to go back to teaching networking. Don't touch that.
I disconnect the microphone. Oh.
5 more minutes, and we go back to teaching networking, okay? You got to go back inside with mommy.
Keep the view.
Whoa, 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 whoa.
Oh, look, we
Messing up the moving table.
to put the
Amelia.
battery and so I can speak the microphone.
Yeah, you want to speak in the microphone? Hold on.
Yeah.
Hold on. All right, speak to the people. Tell them where you're at, what you're doing.
I didn't working.
You're working?
Mm,
What are you working on?
Particle. Da.
What are you working on, honey?
Working on the particle.
You're working on the iPad? Or is this laptop?
A laptop.
This is a laptop, that's right. You're learning about networking? You want to go over some networking stuff?
I got it.
Look at this. See, the switch? Oh, honey, let me go back to the timer so people know when we're going to go back to actually teaching.
Okay.
Don't just eat the microphone.
To speak to me.
Yeah. Look, mommy joined the live stream. Say hi, mommy.
Hi, mommy. There's a lot of particles. I don't see the particles living.
She said hi back.
Hi.
Hi. See right there? Mommy joined.
Hi. You don't talk on the computer.
Yeah, I talk on the computer. You see that bar? Do you have any questions about switching?
Yes.
What do you want to know about?
Learning letters.
There is letters in switching. There's like MAC addresses that are A through F. Can you say that? Your ABCs?
A, B, C, D, E, F, D.
See, MAC addresses end at F. It's like a burned-in address for your NIC. You know what I'm saying? Yeah, on your NIC card, your wireless NIC, it has a burned-in address.
No.
Yeah, it does, honey. And when you build that frame, it puts it in the source or destination.
A, B, C, T, E, F, D, H, I, J,
Okay.
K, N, M, O, P, Q,
Well, hopefully my students know this.
S, T, U, V, W, X,
Hey,
Y, and Z.
okay.
No,
She's a genius.
Next time, won't you sing with me?
Hey, good job, honey. Look, I think mommy's still watching. Tell her to send 50 gifted. Tell her send 50.
Send 50.
That's right. Tell her to send 50 gifted. You know, get the views up. Tell her to send a like.
So like.
Good job, honey. Send a like. That's true. It's facts. Facts. Send a like.
Well,
See?
don't
Hey, she listened. She liked the vid.
Listen me?
Yeah, she listened to you. We got restricted like within a minute of me teaching this somehow on
Good job, mommy.
the TikTok, whatever. It said it was unoriginal content, me teaching networking. It's someone out there, you know, it may be somebody, who knows? Someone out there has it out for us in TikTok.
Mhm.
Huh. It's a deep state.
I love you more. I love you too.
Aw, honey. Okay, I'm gonna get prepped, right? We only have a minute left, so you ready to go inside?
Mhm.
Okay. Go inside. Come on, sister. break about to be over. Gotta get my voice right. Yeah, if any of you guys got little kids, you know the vibes. They be all up in your business. In a good way, though. Angels. Yeah, they restricted my live visibility immediately. Fucking TikTok. Fucking weird. Trying to put people on game to networking. I want to keep someone down. Alrighty. Let's get back to it. We're about to go over some access points, I think, right now. Clear this off. Clear all drawings. Stop the share. Let's get on our whiteboards. Ooh, did I get rid of that old whiteboard? No, it should be, yeah, it should be good right here. All right, let me unmute for the Zoom. Hold on. I wish I could get rid of this. Oof. Oh shit. How do I get back to where I can get my... Damn, I just messed it up. Hold on, guys. Hold on. There we go. I don't know what it is. I'm not going to present anymore. I'm just going to... I was trying to get this top screen off of it, but I'll have to go into my whiteboard settings so we can have a little more space. But okay. Now, we're going to jump back into it, okay, guys? So we just went over a switch, a router, and a firewall. And that was our 3 network components that kind of like when you start off in networking, what you're going to touch. And the next one we're going to go over, same thing is true. We're going to go over access points and wireless LAN controllers. And I'm going to try to be brief, tell you exactly what they do, the terms you need to be successful for the CCNA. And then I think the last thing we're going to talk about is actually an endpoint, which is crazy. They want you to know about endpoints, but it matters because a lot of times, you know, we think of a server, that's not part of the network, right? That's an endpoint. So let's go ahead and talk about, let me type this out, access points and wireless LAN controllers, okay? Access points and wireless LAN controllers. This is gonna be in the Wi-Fi section, okay? So, first off, when we talk about access points, these are Wi-Fi access points. They emit a Wi-Fi signal, which is just RF, on 3 different bands, 2.4 gigahertz, 5 gigahertz, and now 6 gigahertz. They emit this Wi-Fi signal from the access point out its antennas, its radio antennas. And then Wi-Fi enabled clients connect on that signal, that Wi-Fi signal, and then through their wireless NIC, they send data traffic. The access point receives that wireless signal, will modulate it back into digital, and then when it's, you know, copper, when it's Ethernet, it's going to then send that traffic to the switch. And if it's a lightweight or a cloud-based, it is, you know, wireless LAN controller or a cloud-based controller. It's going to determine how to send that traffic, okay? So let's go over the different types of access points. So we have what's called an autonomous access point, and we have a lightweight access point. And then we also have a cloud-based access point. And really, guys, they achieve the same thing, right? They emit that Wi-Fi signal, and then they connect Wi-Fi enabled clients, and they send traffic to where it needs to go, okay? But what's the key difference? With that autonomous access point, it does everything. So that autonomous access point will do the switching, will do the routing, it'll have firewall functionality, it'll be a DNS, a DHCP server, it does everything. This is the easiest one to learn because it's what you probably have at your house right now. You probably have an autonomous access point at your house you got from your ISP that they came in and set up. It emitted an SSID that's just like a standard one they gave you, whatever, and said, hey, you know, here's your Wi-Fi, here's your internet. And that's it. What you don't know is that it's part of a broadband connection or a fiber broadband connection that's connecting you to like some carrier grade NAT that's sending your traffic out to the internet along with all your neighbors, okay? But that's what an autonomous access point is. Now we talk about like the CCNA exam, and important things to know about this is that an autonomous access point does not scale, okay? It doesn't scale, meaning that we can't deploy and manage 10 autonomous access points for our huge office compound or our huge compound or wherever, or our huge office building, okay? What it can do is it can mesh, okay? It can mesh, so that's like 1 to 3 autonomous access points. And then of course, it does everything. And you will manage this from like a web GUI, managed from a self-hosted web GUI. Now, obviously, like I know nowadays, like ISPs, service providers, they give you like an app, and you're like, that's how you maybe control your access point at home. But it's self-hosted, right? Even if that autonomous access point reaches out now to a cloud or whatever, you know, the CCNA exam came out 5 years ago. I get that these may overlap a little bit now, okay? But that's what you need to know for the CCNA exam. It does everything from DNS, DHCP, routing, firewall functionality, port forwarding for you, like all you gamers out there, right? Alrighty. Now, let me draw something out for you. So how is that autonomous access point going to look? So that autonomous access point, here it is, right? This is how I draw my access points. Don't judge me, okay? That autonomous access point. Inside there, you're doing routing. You're a firewall. And you're doing like DNS, DHCP services. You can even do like storage for like a house or your home or whatever, right? So an autonomous access point is going to be like for SOHO environments. SOHO, yes, real acronym. Small office, home office environments, okay? That's what they're built for. Think 1 to max like 50 users. And then if you want to mesh them, you're like, yeah, I got some more users. I don't want to hire an MSP or IT guy yet. You can mesh them, whatever, maybe get to 100 users. It's built for SOHO. Typically, you're going to connect this to a broadband connection. Okay? You may have a modem in there as well, or connected to a modem, okay? But it's going to be a broadband connection. Now, that autonomous access point is going to emit an SSID, okay? It's going to emit an SSID, a service set identifier. I'll type that out over here. My handwriting, you know, as you can see, not that good. That SSID, guys, and this is true, whether I'm talking autonomous, lightweight, or cloud-based, this does not identify an access point. It's a common misconception. That SSID, write this down if you're taking notes, that SSID identifies a wireless network. So what are we talking about here? Okay, this will make more sense when I go over lightweight and I draw it out. That SSID identifies a network, a wireless network, meaning when I connect to this SSID that's like office, behind it is a subnet, a /24 subnet, potentially a VLAN, a whole network. And then if that access point, because it can do this, emits an SSID called accounting, I'm going to write the whole thing out. That SSID identifies a separate wireless network, okay? It does not identify the actual access point. Now, I bring this up because it's an easy misconception, because you may just be used to your home Wi-Fi where you have one access point and you're like, yeah, that's my Wi-Fi, connect to this, right? And you're just like, yeah, access point, router, Wi-Fi, whatever, okay? But that's what an SSID represents, a wireless network. Now, in Cisco, this is a CCNA exam, an SSID can be represented in ASCII or hexadecimal format. So it can be represented in ASCII/hexadecimal format. And it can be up to 32 characters. Now guys, I get it. You may have worked in like Aruba or Arista or Juniper or wherever, and you're like, well, they allow up to 64 characters. Got it, cool, I'm with you. This is just for the CCNA, okay? Just for the CCNA, up to 32 characters. That's an SSID. Now, a lightweight access point. It's easier if I draw this out, all right? So, a lightweight access point. Here's what this bad boy is gonna look like. See, I'm gonna put my stroke thickness to like 2. Yeah, that's good, okay? A lightweight access point is going to do just one thing for you guys. Emit that RF signal, that Wi-Fi signal, for Wi-Fi enabled clients to connect to, and then pass your data off to the switched network, okay? The switched network. This is gonna make sense. It can do layer 2 encryption too at the device, so it may do layer 2 encryption as well, okay? But a lightweight access point is emitting RF. It could do layer 2 like security for you, and then that's it in a lightweight access point. So I'm gonna write up here lightweight. Sometimes you call this LWAP, right? So this LWAP is going to be connected to our switched domain, our switched environment, our copper, our Ethernet environment, okay? It could be off an access port, it could be off a trunk. It just depends how we deploy it. I'm going the basics for now, okay? Then this switch, these switches, right, may be connected to like distro switches, and then these distro switches will connect off to, I'm just going to put the internet, okay? I'm going to make it simple. ISP. Now these LWAPs, okay? These lightweight access points, they are controlled, they're managed. They're wireless LAN profiles that they're going to emit an SSID for. There's that term again, right? SSID represents a wireless network. It's all controlled by something called a wireless LAN controller. That, since it's not in the cloud, it's lightweight, right? That they define these terms different in Cisco. I know it's all combining now. They deploy this wireless LAN controller on-prem. It's almost like a server. It's like a server with a single pane of glass that its whole purpose is to control lightweight access points and then route your traffic for you coming off, Wi-Fi. So that wireless LAN controller, it can be deployed in high availability pairs. There's so many different, rack sizes and compute for this, how many profiles it can handle, licensing for these wireless LAN controllers, but they all do the same thing. Common one is like a 9800 series for like Cisco, like on-prem stuff, okay? But a wireless LAN controller manages, configures, and controls and onboards those lightweight access points, okay? So, if I have this, if I have VLAN 10, this is my marketing department, okay? Marketing. And that is this subnet, 10.0.0.0/24. And then let's say I got VLAN 20. And this is like our accounting department. This is 10.0.2.0/24. These access points may need to emit for both those networks. They need to emit an SSID profile for both those networks, because they may have marketing and accounting users that connect to that access point via Wi-Fi, right? Via that Wi-Fi signal, via the 802.11 frames. I'm going into that too, okay? So we have this. So we have our VLAN set up and configured all throughout our switches, VLAN 10 and 20. And now I say I need to extend that to my wireless network. So in my wireless LAN controller, I'm going to create a WLAN profile, a wireless LAN profile, an SSID profile, whatever, right? That says, hey, for VLAN 20, I'm going to do all these Wi-Fi settings. I'm going to emit on these radio channels, 802.11n, B, G, 2.4 gigahertz, 5 gigahertz. I have a whole slide dedicated to this, right? I'm going to do this type of WPA2, 3 security, enterprise, pre-shared key with AES, CCMP or CGMP, 128-bit, 256-bit, whatever, right? I'm not writing all that down because we're going to get to it, but we're going to configure that wireless LAN profile. So, VLAN 20, we build a WLAN. For VLAN 10, we build a wireless local area network. And we have all those settings I just talked about, QoS profile, whatever. Like, the list can go on and on. We have a whole wireless section, okay? And then, once I build that, or really prior, I build that profile, I have to go configure that profile for that lightweight access point, which really is just me telling that wireless LAN controller, hey, wireless LAN controller, go apply that setting, go apply those WLANs and emit for that. Go send out a Wi-Fi signal for that wireless local area network. And then this access point will do that. It'll be like, okay, here's my marketing Wi-Fi. I'm also going to emit for the accounting Wi-Fi. Okay, cool. Seems pretty simple, right? So how do these access points get managed and controlled and onboarded to this wireless LAN controller? I'm glad you asked. So these lightweight access points, guys, use something called CAPWAP. CAPWAP. I don't have my slide on me, so I forgot what it's called, like controller access provision wireless access point, something like that, okay? These lightweight access points, when I first install it on the ceiling, and I configure it, connects to my switch, and then it's gonna go connect to my wireless LAN controller. There's like 5 different ways it can onboard there. There's DHCP, there's a DNS setting that you can do it, you can statically set it, it can be from a prior profile configuration, whatever, okay? Many different ways we can onboard them into our wireless LAN controller. But you build 2 CAPWAP tunnels, so hear me out on this. So we build a control CAPWAP tunnel. And it is a tunnel because it's going to encapsulate the actual full packet, okay? It's almost like GRE in that way. So that CAPWAP control tunnel is going to be, oh man, it's not on my slide. I used to know this off the top of my head. It's like UDP port 5246 or something like that. It's on my slide. I'm not going to write it on there. But that's our control CAPWAP tunnel. That all the traffic for configuring the access point, putting settings on there, profiles is going to go through that control CAPWAP tunnel, which can also be protected with something called DTLS. It's like TLS, but it's at like layer 2 instead of like using that TCP IP. Anyways. And then guys and girls, if there's any girls in the audience, we have a data CAPWAP tunnel. We have a data CAPWAP tunnel. And guess what? When my users connect, so when I have a user, here's its laptop, connect to the accounting Wi-Fi, and that user wants to talk over here. This is a basic setup. I know there's Flex Connect and other things like that. These 2 users need to talk to each other. They could be connected to the same Wi-Fi and the same access point, but guess where that traffic is going, guys? Through that data CAPWAP tunnel. And then the wireless LAN controller knows where to send that traffic, right? We don't need to get into deep how it knows that, but anyways, Whew. Okay, that's lightweight. So key things about lightweight. They're managed by WLC, and they really only emit a Wi-Fi signal, and then they can do like layer 2 encryption, okay? So that's like, when we do like simultaneous authentication and equals with WPA3, Wi-Fi Protected Access 3, it gives us that PFS, perfect forward secrecy, our brute force attack mitigation and things like that, okay? Alrighty, that's lightweight, guys. Now, cloud-based, how does it differ? And this is at the CCNA level. So I get we can go into a Meraki dashboard, which now is integrating into a Catalyst Center, and we can go deep into cloud-based access points. But they're damn near the same thing as lightweight, except this wireless LAN controller is put into something called like a Meraki cloud, right? Now that wireless LAN controller, we're saying it's not a wireless LAN controller on-prem, we're managing these access points in the cloud now. So now we have our Meraki dashboard that is managing and configuring all the profiles for that access point now, okay? That's a cloud-based access point. So for the exam, that's the differences you need to know. When we say it's cloud-based, that means we can access that single pane of glass to manage all of our access points from anywhere that has an internet connection, because that's the whole point of the public cloud, right? Is that it's broad access. Whew, okay. I'm gonna go back to my slides now, okay guys? I'm gonna go back to the slides. Let me end this whiteboard, because we're gonna get into controller-based networking. I just killed my Zoom. I don't know why I did that. Okay. I don't know why I just killed my Zoom call. That sucks. I gotta tell everyone to get back in. Hey, sorry about that. I literally just hit end on the Zoom call on accident.
That was me. Okay.
Yeah, it's my bad. Not your internet freaking out or anything. I'll wait till everyone gets back in here. I meant to stop the whiteboard and I hit end like a crazy guy. Okay, we'll continue. All right, I think because Tyler had to bounce anyways. So, just want to make sure on these slides I hit everything. So what is a router? Networking device that forwards packets based on their IP. Cool. Firewall, networking device that filters packets typically at the edge. Multiple different levels, contextual awareness, user behavior analysis, you know. An access point, what is it? A networking device that connects Wi-Fi enabled devices back to the switched network infrastructure. And a wireless LAN controller manages all access points set up in lightweight mode, okay? Alrighty, moving on now. So I didn't want to whiteboard this out. It's just kind of a lot. It's better on the slide. SDN controller. What is SDN? So really nowadays it's combined. There used to be a distinct difference between traditional networking and SDN, and there still is, but in our environments, in our typical enterprise, you're using both kind of. So traditional networking is, in the very basics, is I'm SSHing to a device on my CLI, and I'm configuring that device from the CLI terminal. And I do all my devices like that. That's traditional networking. SDN is I'm managing and controlling that device from some sort of centralized server, whether that be Cisco Catalyst Center now, Cisco SD-WAN, Juniper has Mist for like all of its Wi-Fi, Ubiquiti has its unified control panel, and I'm managing all my network infrastructure from a single control panel. So all my VLAN configuration, all my routing configuration, my firewall, my VPN configuration is done from a single panel. That's the main difference. And how SDN achieves that has really evolved throughout the years. So when we get to our new, our new CCNA version, hopefully it dives into this, but it's controller based. So essentially I deploy Cisco Catalyst Center on-prem as a virtual machine, dedicated appliance, or in the cloud. And then I onboard my, could be access points, switches, and routers into that Catalyst Center dashboard. And then all my upgrades, all my routing policy, my ACL policy, my switching policies, my VLANs are all configured from that control panel. So like a web-based GUI now. And you have like a golden image in there, and how it communicates downstream to the fabric is what we call it. The fabric being like our switches, right? That LAN campus actual hardware. How it communicates to that fabric could be through REST APIs, netconf, southbound APIs is really what we call them, but it's like REST. We have serialized languages that we use to communicate and get data, like JSON and XML. And then from our applications, that's like our northbound side, that's just me at the computer. Again, I'm using like RESTconf or HTTP or REST-based APIs to interact with that centralized dashboard, okay? But really that's what it is in essence, that's all it is, guys. It's just a dashboard that lets us control all of our devices. I'm gonna try to bring into view my Unify console here. Give me like 2 seconds just to show you, because I don't have like Cisco Catalyst Center, like just available for me. So I'll show you an example of SDN with Ubiquiti. Not gonna be on the test. And what you really need to know for the exam, guys, is that controller-based networking does everything I just said. You use RESTconf, you use northbound APIs to talk to applications, to talk to network appliances, you use southbound APIs and netconf or RESTconf as well to apply configuration from that centralized dashboard or server. Without giving away too many public IPs and too much stuff so I don't get hacked. Oh look, ISP is using carrier grade NAT, just what I talked about, right? So look at my gateway IP, a 192.168. Try to hack that IP, right? But this is like my dashboard. So I can go to my unified devices here. I can manage the wireless LAN profiles here. I even have my security hooked up, which isn't best practice, right? My like cameras and stuff, but I can do that all from here from the settings. I have my multiple wireless LANs here that represent VLAN 10, 30, 107, and 20. And each access point is emitting an SSID that identifies those wireless LANs that I control from this dashboard. And if I had my other one online right now, it's like kind of my test one. It's not online right now. I could control like 10 different routers and campus and LANs all from this dashboard. That's SDN, right? That's SDN in essence. All right. Let's go back here. All right, final one, an endpoint. Because this can be a little confusing, right? Like if you're a network engineer, I used to think, oh, the server, is that like my responsibility? Now again, I was in the DoD and the Army, so like the training wasn't the highest of speed, the best. But I'm here now to define that for you. An endpoint is any device, printer, server, cell phone, laptop, desktop, that connects to your network infrastructure, okay? VTC machine, which isn't as popular anymore because, we got Microsoft Teams, but that's an endpoint, guys. Anything that connects to your network that is relying on your network infrastructure and your components to do end-to-end communication, server to laptop, laptop to web server, whatever, that's an endpoint, okay? What are we worried about when it comes to our endpoints? That they have availability, that they're connected, that our infrastructure is highly available and redundant and resilient. Whew, okay. A whole lot just to go over network components. Now, the reason I go so in depth, guys, in that first slide is kind of like you get a good baseline, right, of everything moving forward. Okay, I'm going to go over this slide, then we'll take another break because my voice is killing me. So what happens when you try to be enthusiastic. Okay, hardware components. So now we're going to go over like what's in a router. So for any of you guys that have built a PC here, this is going to feel like pretty familiar because it's a lot of the same compute, storage, and network, except in network infrastructure, a little different, right? So thanks, Tyler, I appreciate it. But yeah, that's why these 10 days, I do like a day break because my voice be fucked. Okay, so what's in a router? So a router has a motherboard as well, all right? Just like a computer, you build your PC. With a PC, your storage is what? NVMe and SSD. That's the 1 terabyte, 2 terabytes, or 500 gig storage that hosts your C drive, right? And that's where your operating system lives, in that storage. And then on your PC, you have compute. Well, what are the compute resources in a PC? For gamers, yes, I know you have GPUs, but just bear with me. That's CPU and that's memory. The more CPU, the more memory you have, the more compute processing you can do. The more Chrome tabs you can open up, right? And then you have the networking in your PC. For you guys, for all of us, right? That's your wireless NIC or your NIC. And that's it. Now, a router. And when I say router, I really need to change this slide and let it just say switch as well. A little different. It has all that. But it's purpose built to be a router. So it's going to be a little different, right? We're not having a nice operating system GUI that you can go game on. So no matter what router you have, whether it's an aggregated service router with supervisor engines and service planes and whatever, all these modules, you're going to have some of these basic things. You're going to have CPU. That CPU is going to function the same way it does for a laptop or a computer. It's going to execute the operating system instructions just like a computer CPU. Now, it's not going to have to be as robust because we have other compute things like ASIC chips that do a lot of that data plane forwarding for us. When I say data plane forwarding, that's the actual lift, right? That's the actual getting data from gig 1 out to gig 0. That ASIC chip forwards a lot of that for us, right? It's a compute hardware component as well, but it's different than CPU, okay? Then we have a read-only memory in the router and switch. So what is that? Well, when you boot up a computer and it does its inputs-output checks. So BIOS check, now it's UEFI, secure boot, whatever. It's checking the OEM. It could be doing a TPM chip that checks the hashing on there, whatever. When you boot up in your BIOS, it does input-output checks, so all the peripherals and everything on your motherboard is working, right? It has all the firmware, it's going to work. Router has the same thing. We call it ROM or ROMON, okay? So computer BIOS equals ROMON, read-only memory. This is going to hold the diagnostic software used when the router is powered up. It stores the router's bootstrap program, just like a BIOS, okay? And then we have RAM. Guys, RAM in a router, same as a computer, okay? RAM, random access memory. This is where all of our tables live. I was trying to think of a good word, like not ephemeral, but anyways, all of our tables, like live tables, your ARP cache, your routing table, your MAC address table for a switch, live in your RAM, right? It's live. So when I turn the device off, my routing table is not persistent, right? My ARP table is not persistent. That's what the RAM does. Your RAM is also your running config. I'm going to get into this. So when you boot up that router, and I'm going to go through the boot process, and you get to your CLI, that is RAM. That is your running config, okay? So that's what RAM is. It holds your running config, And then when your device is on, it's hosting that running config. That's what builds your routing tables, all that. And then check it out here, guys. NVRAM, very important. NVRAM, non-volatile RAM. This is a component that's actually going to store your configuration. So NVRAM is a file that actually gets saved on your flash, your storage, just like a file gets saved on your hard drive in a computer. NVRAM, non-volatile RAM, guys, is your stored startup config, okay? It's your stored startup config that's its own file. It's like a text file that lives in your storage, which is flash in a router or switch, your flash. So the flash is a storage device of a router. It holds your operating system, much like an SSD or NVMe holds Windows, Linux, or Mac OS. The flash is the storage for the router that holds the operating system and the startup config. Alrighty, whew. Okay, let's shake it off. So how does a router switch boot up? Here's the boot process. You ready? So I'm gonna power that bad boy on. It's gonna do a post test, okay? I forgot the acronym of what that means. Power on self-test, I think, something like that. That's gonna check the inputs and outputs of the hardware, like a BIOS and the PC. Boom. Our motherboard's good, inputs and outputs are good. We're immediately gonna get loaded into ROM-on mode, guys, or ROM-on, okay? Read-only memory. Read-only memory. That's gonna load the Bootstrap program, and then here's what that Bootstrap program is gonna do. It's gonna search for an operating system. Typical boot process is that operating system is gonna be on the flash. So we're gonna look for like flash, iOS, or disk 0, iOS. Sometimes it's called disk 0. If it's not on the flash, if I don't have a good iOS on the flash, it could revert to doing like a DNS broadcast via TFTP. A lot there, right? Searching for some sort of controller, some sort of server to give me an iOS. If all that fails, guys, we go into ROM-on mode. It's like you get sent to your BIOS. It's just like your computer boots up and you have no image on it and you just go to the BIOS. Same exact thing, ROM-on mode, okay? Now, let's say we don't go into ROM-on mode. So we found a good iOS. Once we load that iOS in a basic startup, in a typical startup, nothing changed, we're gonna search for NVRAM. So iOS loads and we're gonna say, hey, do we have a startup config? Do we have a startup config to load up? And if we do, we're gonna take that startup config, which is our NVRAM, guys, and we're gonna load that into RAM, into our running config. So the startup config that has all of our, BGP configuration, our OSPF configuration, whatever, SNMP, NetFlow, all this configuration that's in the startup config is gonna go into the running config. And then our router is booted up. Say, awesome, sweet. So what else do we need to know about this? And this is real world. So check this out, guys. So this typical boot process, guys, there's something called a config register on your device. That config register, sometimes called confreg, has a standard boot process code. That code, so like confreg, configure register 0x2102. There's a hexadecimal version of this. I don't know, just look it up. That is this. All this right here. And the RAM. Typical boot process, okay? When would you not need a typical boot process? Let's say you fall into equipment. You fall into a router, right? And you try to log into it. You don't know the username or password. So you say, well, fuck, what am I going to do? I can't log in. I can't console in. I need to fix this router. I need to fix this device. If you get access to it, console, you can reboot it, send it into ROM-on mode using like a break sequence. Then from ROM-on mode, you can say, hey, actually big dog, actually router, works for switch 2, a little bit different commands, but do this. This is going to be your boot startup sequence. And you know what that's going to tell it? It's going to say, hey, go ahead and skip this. Nah, no NVRAM. Skip it. If it's there, awesome, skip it. And boot me straight into RAM, okay? And then once I'm into RAM, you have two things you can do. Set a new username and password and save it. That could get rid of your whole startup config because you're overriding it. Or once you're in here, you pretty much password broke, your router now. You're in there. You do copy, startup config, to running config. You load it up. Hopefully there's no AAA in there. It's going to mess you up. Or you could just straight up, set up TFTP, send that startup config, edit it out, TFTP a new one in, replace it in the flash, whatever. There's so many ways to do it. But you can do this, and then you can start, or you can configure a new username and password. Okay? And then once you do that, from global config, you send it back to the normal boot sequence with this command, config register 0x2102. That's why it's important to know this boot process, okay? All right, let me clear these drawings. And let's go ahead and take a look at where we're at, guys. So now we need to go over network architecture, control and data plane, and the OSI model. Let me check our syllabus. Hold on. Where we at? So we got to get through here. Oh, yeah. Ooh, we got to get to IP addressing. That's a tough one. Okay. I'm going to take a break, 10-minute break. And then when we come back, I'm going to go over these three. We'll take another break, and we'll do IP addressing and IPv6 addressing tonight. If I can't get to this, guys, it may just be homework, okay? And if I can't get to IP addressing, that'll just be for our Tuesday session, and I'll just do that, okay? So, sorry, I've been a little long-winded. All right, I'm going to take a break. I'm going to mute myself.
Hey, John, just, I'll cut out here, catch up, and then see y'all tomorrow at 17:30.
Okay, I'm going to put us in that signal chat, and then I'll tell you which videos to watch, okay? I'm going to record this too, and I'll post it on the Google Drive. But if you want my YouTube videos versus the live session, I'll just give you the option, okay?
Okay, you mind either emailing me or Teams me?
Yeah, I'll talk to you about that. I didn't want to Teams you from my work computer. Anyways, I'll text you. I'll email you about it.
No,
okay?
you're good.
Yeah.
I understand. Yeah.
Okay. All right, bro. Okay. A little break here, guys. I'm going to get some water. All right. Sorry if you hear a lawnmower out there. My neighbor cuts my yard for me. Well, I pay him, but he decided to do it today, which is okay. It's okay, But I teach out of my garage actually, which I've insulated and put AC, but it's still fucking hot. The AC, I didn't turn it on until I first started. But yeah, sorry if you hear all that noise. All right, let me check the YouTube. Let me check the YouTube channel. Jet engine starting older equipment. Yeah, facts. Yeah. When you light up the 2900 or old 3800 switch, yeah, it's a jet engine. And especially servers, like the old Dell PowerEdge. Whew, those things would be brutal. Yeah, I gotta figure out, fucking TikTok, man. I hate TikTok as a platform sometimes. Somehow restricted my live stream. I don't even know how. I gotta go appeal it now. Because I feel like this would be good content, good live content. Yo, Trey, I don't know how to do that, bro. I'm on my computer, so I don't know how to invite you, and then my phone is the camera. If you're still in here. I mean, it's been a while. I didn't want my Zoom clients to, think I'm choosing the TikTok chat over, let me see. Yeah, I don't know how to do this shit from the TikTok studio, bro. You know, I'm like, I don't know. I'll try to figure it out tomorrow, then I can add you. I don't even know how these gifts work either. Like, I see this like thing, the real Catherine Rosas. I don't. Thanks. I think you sent me something. I don't know. I don't know what the fuck. Or new followers, gifters. I'm like Boomer, dude. I'm unk status when it comes to this shit on TikTok. All right, I'm gonna stop talking now so I can take a little break. Okay, let's see. Let's make sure I don't get restricted again. I was on live, and TikTok for some reason restricted my live. I have no idea why. It said it was unoriginal content, even though I've made all this content myself. This time I didn't put like Cisco in the titles and stuff, so we'll see. We'll see how it goes. Okay, let's start off with the whiteboard, huh? Shit, I didn't mean to do a new one. It's okay. Alrighty, guys. Let me get my Zoom chat. Okay, guys. Now we're going to go over network architecture. So now we're going to go over the basics like LAN, WAN, and I'll do that on the slides. But what I want to go over with you guys is something called the collapsed core and a 3-tier core topology, and also spine and leaf topology. So let's do it. So we're going to talk about network architectures here. Network architecture. So it's broad, right? It's meant to be broad because this is for our purposes. This is going to be going over what Cisco says, right? This is going to be Cisco based. So the first one we're going to talk about is the 3-tier topology, okay? 3-tier topology. 3-tier topology. I'm going to say it a couple more times, right? All right. So this is going to have a core layer, a distro layer, and an access layer, all right? And we're going to go over the differences in those layers. So at our core layer, I'm going to do this with my pen, do black here. At my core layer, these are going to be our most robust core layer switches. Now imagine this is for a large campus network. This is large enterprise, large campus. So when we talk 3-tier core topology, large, okay? Large enterprise. It matters. The wording kind of matters there. So we have our core layer. Our core layer. Now these are going to be robust switches. Think like Cisco 9600s. Back in the day, this was like 6500 core switches. These are going to be robust because they're going to aggregate everything up to the WAN. This is going to be your internet layer, really. It could connect to routers, or these core layer switches could connect you straight off to the ISP itself, okay? So these core switches go to the ISP. And typically, these core switches, maybe they're like multiple switches stacked, or they could just be a switch itself, right? A really robust switch with like multiple levels, multiple U's, okay? Think of like an 8U or 16U switch. So this is going to aggregate all traffic out to the internet. It's also your demarc point. Then we're going to have distro switches. This is going to be your distribution layer. Okay? I'm just going to shorthand it for distro. This is our distro layer. That's how you're going to hear it, like campus network, you know, in the real world distro layer. This distro layer is going to do all your ACLs, all your routing for your users. It's going to do all your route policy. It can do NAT for you. This is where all your user traffic is going to be aggregated. And if you have like a web server farm or a bunch of servers, like in a comms closet, you have a bunch of compute and stores that you have on-prem, local, that's where that's going to sit, okay? So in these distro switches, typically it's like layer 3 here. It could be trunks, could be. We could do something like SVL, SSO, NSO, nonstop forwarding, or NSF, excuse me, nonstop forwarding, stateful switchover, or they could not be stacked at all, okay? This could just be its own 93, 9400 Cisco Catalyst switches. Now, in these distro switches, this is all of our routing. So for all of our VLANs, we'll have SVIs, switch virtual interfaces. So we'll have interface VLAN 10, 20, 30, 40. That's doing all the routing for our users that are connected at our access layer, okay? Then we have our access layer. These are access layer switches. And you guessed it, you know, if you're good at deducing things, the access layer is where we plug in all of our endpoints, okay? This is where all of our endpoints plug into. This is going to be where our computers, our printers, our access points as well plug into, okay? So, laptops, access points on the access layer. Just makes sense, right? Printers are at this access layer. And there's typically going to be these redundant connections. Now, depending who you ask, depending what network architect, what design course they went to, and it's also like by per use case, typically it's going to be a layer 2 trunk up to our distro layer. And that's where all of our routing is. Remember, at the distro layer is where all of our routing is. So some key things though, some key things. Remember that 3-tier core topology for large enterprises, okay? Large enterprises. That's the key term there, okay? Large enterprises. 3 layers. Core distro access. Core being like for the internet, your WAN aggregation. Your distro is going to be doing all the ACL, all the security policy, all the routing policy for your downstream users here. Then the access layer is where you're going to actually plug in all your endpoints. When we say endpoints, we don't mean like our server farm over here connected to maybe a data center or on-prem. We mean like laptops, printers, access points, computers, okay? Think if I'm missing anything here. And it's typically trunked up to that distro layer. Okay, so that's the 3-tier core topology. The next one we're going to talk about is our collapsed core. Our collapsed core topology. So with the collapsed core, this is for small to medium-sized companies, organizations, enterprises with minimal growth expectations. Okay? With minimal growth expectations. That's another key term here, okay? So this is like maybe up to 500, 1,000 users. I'm not going to put a specific number on there, but this is a medium-sized business. Could become large, but there's not a lot of growth in the future. We're not building a topology that's going to meet scale in 5 years. This is, hey, this is where we're at. We need this kind of topology to meet our current demands. We're not planning on large exponential growth. So core, collapsed core, pretty simple to understand. Let me zoom this out so maybe you can see it. It's a little small. Essentially, we just collapse our distro and our core. So this could be any kind of hardware you want, 9500s, 9400s, whatever. But this is going to be our core/distro layer. Okay? Core/distro. That's the collapse here. So now, this could be also our WAN aggregate out to our ISP and our DMARC point. And it's also going to be doing all of our routing policy, security policy, and ACLs for our downstream, for all of our endpoints plugged into, you guessed it, our access layer, guys. Our access layer, okay? So key things there, small, medium companies with minimal growth expectations. I'm going to go back to the slides now. I'm going to go back to the slides because now we're going to go over spine and leaf, LAN and WAN. A little bit easier. I don't need to draw that out for you, and you can actually take your proper notes, right? So let me end the Zoom call here. Or it's not end the Zoom call, excuse me. End the whiteboard session, and let's present our network architecture slides. Okay. So a LAN, more network architectures, a LAN, so simple, so easy. That's a local area network. There's a collection of devices connected together in one physical location. And the term LAN, local area network, is kind of used broadly because I could have a campus network with so many different VLANs, so many different subnets, routing policy, GPOs out the craziness, right? All these VLANs, multiple spanning tree, whatever. And that's still a LAN. It's still in one geographical location on my campus, and users are in my LAN there. It's a campus network. It's huge, thousands of users, but it's still a LAN, okay? It's local to a geographical location. Now, obviously for you brainiacs in the audience, you know that these LANs can now be extended using VXLAN. So you can extend LANs beyond a geographical region. But in the CCNA exam, we're going to keep it just at that, okay? It typically describes like the layer 2 infrastructure, but it can be used, and I've heard it be used even in my day job, like, oh, that's on the LAN, right? And even though it's connected to my multi-layer switch that's doing some routing for me, but it's on my LAN, right? Now the WAN is pretty specific. A lot of people get this wrong too. A lot of people think this is like synonymous with your connection to the internet, to the ISP. Not true. So a wide area network is just a collection of interconnected local area networks. So I could take 2 routers right now. Right now I could hold up 2 routers in my hands. I could connect computers to them on the left and right side, but in between, connect a Cat5 between those two routers. And guess what? That connection between those two routers is a WAN because it's interconnecting LANs. It's giving LANs the ability to talk to each other over the WAN. That's a wide area network. Okay, a MAN, we're going to skip that. It's not really important for our purposes. All right, what's a SOHO? I brought this up earlier in the course. So a SOHO, small office, home office, these are simplistic and focus on cheap availability for the customer. All we're saying here for the small office, home office is you have a little offshoot, 3 to 5 users, 10 users, 20 users, whatever, and we're just putting an autonomous access point in there, connecting it to the ISP modem. We may mesh it, whatever, and it's going to serve all of our users there. Hook up a printer there, a little storage there. Key thing is that a SOHO network, multiple users share a single broadband connection. So it's a single broadband connection. So in here, like, if I were to take my pen and I combined all this into a single like access point, guess what? That's a SOHO network, okay? All right, 3-tier core topology. If you want to take your notes, go ahead and take your notes. We already went over this on the whiteboard, but again, I kind of already described that. Collapse core, already went over that as well. Now, spine and leaf, which is very important. If you guys have been keeping up with AI and how robust these AI data centers are and how they're destroying our land, no big deal, just destroying water and destroying everything America stands for. Not just kidding. But if you actually looked into how networking is, it's pretty much building off this. It's building off all these multiple nodes of high redundancy, high availability, and it's switching so quickly in these AI infrastructures. It even uses something called InfiniBand sometimes, and different OSs called like Sonic. That's like kind of like the standard one happening right now. Anyways, it builds off this though, the spine and leaf, which was built for data centers originally. And in a spine and leaf architecture, devices are separated by the same number of hops. So in spine and leaf topologies allow for consistent latency among network devices. And if you can see here, this leaf node, because now in data centers it's like a node rather than like a switch, right? Sorry if you hear that, it's my youngest. Hi, baby. A leaf switch is connected to every single spine switch. So there's redundancy, right? So that means that, if one spine goes down, it really doesn't matter for my leaf switch because I still have connectivity to all my leaves, okay? That's the big thing with spine and leaf. And then when we're like doing like Catalyst Center and we're provisioning thousands of devices, 1,000 leaf nodes, that consistent latency is so important. For our scripts that we're running from wherever we're running them from, maybe we don't want to run into race conditions. Maybe we need to apply profiles all at the same time to all of our devices. That consistent latency you get with that spine and leaf is a good architecture, even when we're deploying like Catalyst Center for the enterprise. All right, the boring stuff back in the day, we'll talk about it. Star topology, type of network topology in which every device in the network is individually connected to a central node. Full mesh, highly redundant, the most redundant. A full mesh topology is when every network node is fully connected to each other within a system or domain. Sometimes, we still got this. Sometimes we do like phase 3 DMVPN, and technically that's full mesh because all of our spoke sites in DMVPN can actually know where to go based off the NBMA NHS mappings during phase 3. More on that later. But full mesh, right? It could also just be done on our LAN as well, a full mesh topology. Okay, and then a bus topology. Super old school, right? A bus network is a local area network topology in which each node, a workstation, or other device is connected to a main cable or link called a bus. That's where, to break that down, guys, so I don't just read off the slides. Every device is connected to like one way, this bus, it's like back in the 90s. This one way kind of like pillar, you can think of it, and one computer talked, and then the other 3 had to wait. Right? It's kind of like almost like back to the half duplex days. That's a bus topology. I don't know if you'll see it on the exam or not. I don't know, or I can't talk about it, but Alrighty, let's shake it off. We're about to dive into control and data plane now, and we're gonna jump into it. I'm gonna get that CCNA quickly off my screen there. Okay. So to first talk about control plane versus data plane, we need to kind of address traditional versus controller-based networks again. So in traditional networking, that device, the router, the switch, whatever, the control plane, the data plane, the management plane are all running on that device. And what I mean by that is I'm configuring technologies and protocols on that device like OSPF, like LACP, like BGP, like MSDP, whatever, right? And all that device has all those technologies and protocols to inform it on how to forward the actual raw data and traffic. So it informs our data plane. I go configure that in traditional networks. Traditional networks, I CLI, I get into that device, and I configure those control plane technologies and protocols. And then that control plane kind of informs the device, the data plane, how to forward traffic. It builds that forwarding table, that fib. So we also have a management plane, not technically in here right now, but that's like, think like your VTY lines, SNMP, stuff like that. Anyways, okay. Controller-based networking. It separates that. It decouples the control plane. So what are we talking about here? What do you mean it decouples the control plane? Well, now I'm going to step away from the screen, guys, just for a second while I talk, because my daughter turned off my AC in my garage. But the control plane gets decoupled in controller-based networks. In controller-based networks, the control plane is all centralized. Like I showed you with my unified dashboard, I went into a single web GUI, and all that configuration, all that protocol, that technology was done from a single pane of glass, from a single web GUI. Wireless LAN controllers have kind of been doing this for a while now, right? So in controller-based networking, the control plane is decoupled, and it's all at that single SDN appliance, which is like Cisco Catalyst Center or the Cisco SD-WAN appliance, okay? Or like my unified dashboard, but we're talking Cisco here. So why is this important? Because when we talk controller plane versus data plane, the reason the exam wants us to know about the differences is kind of for what I just described. Like, when does the control plane get decoupled and centralized in controller-based networking? So you can see here traditional networking, like a switch, it has a control plane and data plane, all right there. But in controller-based networking, the control plane all goes to the network controller. And then the data plane still stays there. Like, obviously the data plane's always going to be at the device because my computer is directly connected to that device, sending an electrical signal in my Ethernet standard, going to the switch modulates that back into digital, that electrical signal on the copper wire, or like, maybe it's fiber, whatever. And then it has to forward out my interfaces, and it uses like an ASIC chip to actually do the forwarding of that packet. That's the data plane. It's still right there in our fabric underlay, kind of using SDN terms. It's all right there, right? We still need that data plane. But what informs the data plane on how to switch or how to forward, the control plane protocols and technologies are now decoupled and then centralized into a SDN appliance, network controller. So just more kind of how it works in the data plane, right? So there's our control plane. This is just an example of like OSPF. We have the OSPF routing protocol. It builds a neighbor table. It builds a link state database, so like a database. That informs the routing table on all the networks it knows about and how to forward IP-based traffic. And then the routing table, our RIB is what it's called too, routing information base, informs the FIB, our forwarding table, or Cisco Express forwarding table, or FIB, forwarding information base, how to actually switch those packets out the router. Like how to actually, if it's incoming here, go outbound here. And that's how it quickly switches those packets out the router, okay? Alrighty. Do we have time to go over OSI model before I take our next break? I think we do. I think we're good, guys. Okay, OSI model. So the OSI model describes how we encapsulate a packet end-to-end from layer 1s to layer 7, okay? It describes data encapsulation. It's also kind of like the basis for troubleshooting. It's when you start troubleshooting, as network engineers, do we start at layer 7? Oh, it's the application. No, I've had to do that. Don't get me wrong. I've had to prove through a Wireshark capture, decrypting TLS on a Wireshark capture. It's really cool. There's a great YouTuber out there that Chris Greer shows you how to do it from like a workstation where I proved that it was the VM Horizon VDI client HTTPS connection that was breaking. It was not my network. I wasn't blocking anything. So I've had to do that before, but the OSI model helps us define how things get encapsulated, where the technologies are in the encapsulation process, and then also helps us troubleshoot as well as network engineers. Here's the 7 layers. It's not the prettiest, I know. My Network Plus course actually has a prettier one. I need to transfer it to here. But here's the layers. I don't know the silly acronym, guys. I'm sorry. It's like please something sausage pizza away. I don't know. I don't know the acronym. I just memorized the OSI model. I probably should do that though from beginner learners. Anyways, so where do we start? Layer 1 and 2, the physical layer. My thing is the most boring layer is what it is. Some people love it, but the physical layer, that's our cabling, that's our fiber, that's our copper, Ethernet, our twisted pair, unshielded twisted pair, our category 5, 6, 7, whatever speeds, our multi-mode, single mode fiber, and then all the fiber connectors, LC, SC, all those things. And then wireless, guys, the actual Wi-Fi signal, like the Wi-Fi emitting signal, the RF on that 2.4 gigahertz, 5 gigahertz band, that's layer 1, technically, because that's what connects Wi-Fi enabled devices to that access point initially. It's like a cable, but it's a Wi-Fi signal you can't see. Okay. Layer 2, the data link layer. This is where our switching happens. This is where our MAC address happens. This is our data link layer. When we're working in layer 2, we call it frames, okay? Frames. It's going to forward based off MAC addresses. Our layer 2 switches forward based off the destination MAC address, which they base off the MAC address table that gets populated based on the source MAC address, okay? The Ethernet standard, we're talking like 802.3, that actual encapsulation standard of Ethernet is also layer 2 as well, okay? It's an encapsulation standard. A lot of times people use Ethernet just to say like a cable, but really a cable is copper unshielded or shielded twisted pairs on an RJ45 connector with different category standards. Ethernet is the actual encapsulation technology based off the request for comment standard 802.3, okay? Layer 3, the network layer. So this is IP addresses. This is our routing. This is IP-based packets. This is that layer 3 header with the source IP and the destination IP, okay? And then layer 4, that's the transport layer. This is where we do TCP and UDP. We're going to learn about the three-way handshake. The TCP three-way handshake is how we do unicast connections across end-to-end to make sure our data channels are established so we don't lose packets, we don't have packet loss. It does something called a three-way handshake. We're going to learn about that. In the TCP header, there's SYN, ACK flags, SYN-ACK flags, FIN flags, all sorts of good stuff, okay, where we're going to go over. And that's TCP and UDP. Layer 5, the session layer. This is going to manage the sockets, and that's actually where like TLS is done as well, guys. So like the session layer, layer 5, when we start that TLS handshake, that comes after the TCP three-way handshake. So like after layer 4, then we move into like our session layer. That's like TLS, SSL. It's also in layer 6 as well, but presentation layer. And then really the next important one I'm going to go over is the application layer. That is our actual like applications, guys. It's really hard to think about when I first started this. Like the application layer, layer 7, the hypertext transfer protocol, the actual HTTP protocol that is able to send web files to your Chrome web browser is layer 7. That's application, okay? We ensure that that HTTP protocol can reach end-to-end to do those file transfers essentially from web server to web browser at your workstation through our IP, TCP, and TLS sessions, okay? Which we also need the layer 2 before that and the layer 1 before that. Now, I'm going to deep dive into layers 1, 2, 3, and 4 because as network engineers, that's where we live, right? Yes, we have to troubleshoot application layers sometimes, but that's where we live. Layers 1, 2, 3, and 4. So layer 1 is where most troubleshooting begins. At layer 1, you will see cyclic redundancy check errors, EMI, distance factors, missing pairs in copper, and incorrect SFPs. That's like some basic layer 1 troubleshooting. As you see here, here's like a cabling standard for like our RJ45, shielded, unshielded, twisted pair of copper cables. Here's some fiber connectors here. And then we also use coax copper as well. That's like in our modem connections. And then for fiber, we have multi-mode, single mode. So single mode is that core glass, that glass core there, which is 9 microns in diameter. Okay, go ahead and write that down. That single mode glass core is 9, whoa, what am I in? What's my font here? Let's go black. Is 9 microns in diameter, okay? I'm just going to say diameter. And then multi-mode is going to be 50 or 62.5 microns. Okay, that's like the unit of measurement there, right, guys? Oh, I can't grab this? Yeah, there we go. Alrighty. So that's some fiber for you. And single mode is going to be longer distances. Where multi-mode is going to be shorter distances of like 550 meters. Where single mode can, depending on the single mode fiber you have, go up to like 70 kilometers, right? With copper, shielded and unshielded twisted pair are RJ45 connections in the Cat 6 Alpha, Cat 5E categories up to 7/8. Typically the distance is capped at 100 meters or 100 yards, okay? And then there's two cabling standards. So when you're making your RJ45 ends, it's T568 Alpha and T568 Bravo. On the screen, I have the T568 Bravo standard here. Orange, white, orange, blue, white, blue, or excuse me, green, white, blue, blue, white, green, brown, white, brown, okay? We all have Google at our disposal. You can just look that up if you ever actually forget, okay? That's our cabling standards. And yes, they have to be the same on both sides. So if you make a 568 Bravo on one side and 568 Alpha on the other side, that's not a straight through connection. It's not going to work, right? For the slower speeds, like fast Ethernet, 1 and 2 were transmitting, and pins 3 and 6 were receiving. Kind of old school now. When we do like gigabit speeds, now like all 8 pins will be, well, 4 will be transmitting, 4 will be receiving, and then all 8 could be used for like PoE, okay? Whereas like old school fast Ethernet, you see pins 4 and 5 and 7 and 8 were for PoE, then 1 and 2 and 3 and 6 for transmitting that Ethernet data. But there's so many different standards for it now. Just like wanted you to be aware that the pins do have a purpose depending on where you're at. You could be on some legacy equipment one day, like working on Ethernet or fast Ethernet. Okay, layer 2. I beat you over the head in this in the first session. So layer 2 frames the data link layer. That's where switches are. They build a MAC address table. That MAC address table gets built based off incoming ingress source MAC addresses, and it forwards layer 2 traffic based on the destination MAC address based on what the MAC address table tells it. Boom. Let's go. Layer 3. I beat you over the head with this too in the first 30 minutes, hour. It's layer 3 communication, all based on IP addressing. A multi-layer switch or router is going to do our layer 3, and it's going to forward IP-based packets based off the information in the routing table with the source IP and destination IP in that layer 3 header. Then layer 4. Layer 4, our transport layer, has TCP and UDP. TCP, for testing purposes, is reliable, okay? It's reliable. UDP is unreliable. Doesn't mean UDP sucks. It means they're purpose-built for different types of traffic. With TCP traffic, that's more for like web browsing. That's for like, I need every single file, every single bit, I'm gonna use TCP. Now with UDP, I'm gonna use that when I can afford some packet loss. What I mean by we can afford it is that through voice or video traffic, if I'm on the freeway going 8 miles an hour between cell towers and I drop some packets based on just the RF connection, that 5G LTE connection to a cell tower miles away, if I drop packets, I don't want my session completely dropping. Everyone would have drop calls. There'd be no call. There'd be no telephones, right? There'd be no VoIP. TCP is the opposite. TCP, the moment you start losing bits in that data channel that's established after our three-way handshake, it rebuilds. You rebuild that data channel before you start sending and receiving traffic, okay? So in that three-way handshake, the sender initiates a TCP session with a SYN flag. The receiver, like a web server, receives that and acknowledges that SYN flag. And in the TCP header, that layer 4 header sends back a SYN-ACK flag. The sender then sends back an acknowledgement saying, I got your SYN, I'm acknowledging that. And then their TCP connection, their data channel is established. And then they can start forwarding or downloading, uploading traffic. And then during that downloading and uploading, guys, if there's packet loss, we're gonna reestablish that TCP connection. We have to reestablish it. So we could have something like TCP window scaling, which I go over this in another section later, like on the whiteboard, where I'm downloading like a video game, I'm getting 10, 20, 30, 40 megs of speed, 50 megs. And then all of a sudden you see me drop down to like 5. That's TCP window scaling. When we started downloading so much traffic in our TCP data channel up to 50 megs, that somewhere along that end-to-end path, we got packet loss and TCP brought us back down to 5 megs. Now there is a way to keep that stable. Of course, there's a way to keep that stable where we stay at like a certain packet, not packet loss, but a certain level, like, hey, we're gonna stay at 30 megs, okay? That's like WAN optimization. That can be built into the TCP header now, or we could have like a dedicated appliance to do it as well. Now UDP, best effort can do unicast, broadcast, and multicast traffic, whereas TCP only does unicast. And UDP does not establish a data channel. It doesn't have a big layer 4 header, like the UDP packet header, I think is like 8 bytes. It just does like sequencing checks, really, where the TCP header is larger, more overhead, and it has all those like fields for the SYN ACK flags and priority fields and things like that. Okay, so that's going to be it for OSI. I'm going to go ahead and take another 10-minute break, rest my voice, and then we're going to continue, guys. All right, guys, I'm going to end the live stream. So I'm going to do the last 20 minutes with my Zoom callers. Since they paid for it, they get lab access, things like that. So I appreciate anyone that tuned in. I appreciate it. My voice is gone now. Fucked, because I was trying to be too enthusiastic and loud. So I'll see you Wednesday. We're going to go live Wednesday again. And hopefully we don't get immediately restricted like I did in my first live stream.